So, not long ago, a paper came out claiming to have definitive proof that our universe cannot be a simulation. I mean, this seemed to finally settle one of the biggest, most mind-bending questions in all of science. But today, we're going to dig into a brand new, very rigorous counter-argument, and it all comes down to one critical detail. What if we've been using the wrong definition of simulation this whole time?
And this was it. This was the powerful conclusion from that 2025 paper by Faizal and his team. They took some of the absolute deepest theorems in mathematical logic, wove them together, and argued that the whole idea of a simulated universe was just mathematically impossible. Seems pretty open and shut. Case closed, right?
Well, maybe not so fast. You see, a counterargument from Ariano Peña is saying that this entire beautiful case rests on a hidden assumption about what a simulation even is. And if you change that one little assumption, well, that might just change absolutely everything.
Okay, so to really get why this new idea is such a big deal, we first have to appreciate just how strong the original argument was. It's a really powerful case built on the absolute bedrock limits of what logic and computation can ever hope to achieve. What you're looking at here is basically a century of some of the most brain-breaking discoveries in the history of mathematics. These are called limitative theorems, and they're just profound. To put it simply, they prove that any formal system, you can think of that as a computer program or a set of physical laws, if it's powerful enough to do basic arithmetic, it will always be incomplete. There will always be things that are true that the system itself can never, ever prove.
And here's how they built their case, step by step. The logic feels completely airtight, right? Step 1, a theory of everything would have to be an algorithm. Step 2, but we just learned from Gödel and the others that no algorithmic system can ever be complete. Step 3, any simulation of our universe would have to be algorithmic. And boom, the conclusion, no simulation can possibly capture the entirety of our universe's physics.
But what if that third step, that crucial assumption that any simulation must be algorithmic, is where the logic stumbles? This new counter-argument we're digging into claims that this seemingly perfect logic actually commits a very subtle but absolutely critical error, a flaw that logicians call a quantifier overreach.
And this, right here, is the absolute heart of the rebuttal. The original proof is brilliant, it's correct, but it's only correct for one specific type of simulation, an algorithmic one. The mistake, the overreach, is then taking that conclusion and applying it to all possible simulations that could ever exist. The new paper argues that this is a leap too far, because it just assumes all simulations have to be of that one specific kind.
Now, to really get your head around this, the new framework uses this incredible analogy, the difference between the map and the territory. The territory, that's the real deal, reality itself, the complete underlying source of everything. The map, on the other hand, is our scientific model of it. It's a limited, projected, incomplete representation. Those undecidability theorems, they apply to the map's inability to fully describe the territory.
And this isn't just some loose metaphor either. A new framework called TCGS, which stands for Theory of the Counterspace and its Shadow, gives this idea some serious mathematical and geometric muscle. In this model, the territory is pictured as a higher four-dimensional reality they call the counterspace. Our observable three-dimensional universe is just a shadow that's projected from it. So what does that mean? It means those unprovable Gödel sentences we talked about, they actually have a physical meaning. They are truths about the 4D source that are simply invisible from our 3D shadow.
You know, this view totally reframes what science is even for. A failed experiment isn't some dead end. It's not a falsification of reality. It's a clue. It's a discovery that our map is incomplete. In this model, science becomes this endless, amazing process of cartography, of constantly refining our map to better approximate a territory that is fundamentally richer than any map we could ever hope to draw.
Okay, so if we accept this split, you've got the map on one hand, the territory on the other, then it follows that trying to simulate them are two completely different jobs. And this leads us to a really critical distinction between two very different kinds of simulation.
On one side, you've got an algorithmic simulation. Its target is the territory itself, the 4D source. Its goal is to compute all truths from a basic set of rules. And as we've seen, Gödel's theorems prove this is flat out impossible. But on the other side, you have a projection simulation. Its goal is way more modest. It only tries to approximate what we can actually see and measure on the map by solving the laws that work there. It makes no claim at all to capture the full truth of the deeper source.
So can we actually simulate the map? Well, the answer comes down to a mathematical property called well-posedness. It's a bit technical, but basically it just means the laws of the system are stable and predictable. Think about it. If the laws were ill-posed, the tiniest change in the starting conditions would create a wildly different result, making any kind of prediction or simulation totally impossible.
And here is the absolute kicker. The laws that govern our map, our observable, 3D universe, are well-posed, and that means we can simulate them. Even if the full 4D source is some non-algorithmic, uncomputable beast, its 3D shadow, our universe, is perfectly, operationally simulable.
Now this is where things get really wild. Because if our 3D universe really is just a projection, a shadow of some higher dimensional reality, then maybe, just maybe, some of the weirdest and most mysterious features of our cosmos aren't really things at all. Maybe they're just geometric artifacts of that projection.
So for example, dark matter. Maybe it's not some weird exotic particle, but just the gravitational effect of the 4D geometry warping our 3D map. The apparent randomness of evolution? This framework suggests that might just be what we see when we take time slices of a fixed, deterministic 4D biological structure. And quantum duality? The fact that things can be both a wave and a particle? What if those are just two different incompatible 3D shadows of the same underlying 4D object?
Now, an expert watching this might be thinking, hang on, isn't this just a fancy version of MOND, or modified Newtonian dynamics? The counter-argument is a firm no. You see, MOND works by modifying our existing 3D laws to make them fit the data. TCGS, on the other hand, tries to derive those laws from a higher 4D geometry. But the biggest difference is how they see time. MOND treats time as fundamental. TCGS sees time as just an artifact of the projection. They're not just different theories, they are describing reality in fundamentally different ways.
Okay, let's pull this all together. After this deep dive into logic and physics and geometry, where do we land? Can the universe be a simulation or not?
The final verdict seems to be that the original conclusion was a quantifier overreach. The statement, "the universe cannot be a simulation," is just too broad. The undecidability theorems prove something much more specific and much more subtle, that the universe cannot be an algorithmic simulation of its own fundamental source. But that leaves all sorts of other possibilities wide open.
And this chart really just nails the difference, doesn't it? The original argument reached this huge, sweeping conclusion, ruling out all simulation entirely. The counterargument doesn't actually refute the core logic. It just corrects the scope of that conclusion, showing it only applies to one very specific kind of simulation.
So we're going to end on this thought. This whole debate over the simulation hypothesis has actually led us to a much deeper question about the nature of science itself. If our theories are just maps of a shadow, then what does a failed prediction really mean? It's not an end, it's an invitation. A clue that's pointing us toward the deeper, richer, and maybe, just maybe, an ultimately unmappable territory that is reality itself.